In the previous two videos, we've looked at how do we make a compound that has an alkyne in it, right? And so we've come up with two different ways of doing it. One, we can start from an alkene. We can do bromination followed by elimination with a very strong base to make the alkyne. The other option was in the first video of this week, where we start with a terminal alkyne. We treat that with a very strong base to make the conjugate base, and then we use that conjugate base as a nucleophile in an SN2 reaction. So those are the two ways, if we need an alkyne as a starting material, those are the two ways we're going to make that alkyne. And then once we have an alkyne, now we can do other reactions going forward. So this video is all about what are the other reactions we can do once we have an alkyne moving forward, right? What can we turn that alkyne into? For the vast majority of these reactions, we are going to be talking about additions, right? Alkynes and addition reactions. So if you have your list of addition reactions from a couple exams ago, that's going to be useful. So first of all, let's just start with, we'll start with an easy one. What happens if we react an alkyne with Br2? If you had to predict, you would say, well, we're going to get rid of one pi bond and we're going to have one bromine on one carbon and one bromine on the other carbon, and you're exactly right. That's exactly what you would get, is you would get a bromine here and you would get a bromine here, right? So this is very much like the bromination of an alkene, except that we have two pi bonds here, so we're going to react it once, and then if we react with the second equivalent of Br2, it's going to happen again, right? Because now we just have an alkene. We're going to make the bromonium. We're going to have the bromine come in and attack. And what we're going to end up with is we're going to end up with overall 4 bromines attached to these 2 carbon atoms, where the pi bonds have, both pi bonds of the alkyne have reacted, right? And so this is kind of a general trend of alkyne reactions. What's going to happen is our first equivalent of whatever we're reacting it with, in this case Br2, will reacts with 1 pi bond, right? To make an alkene product. Right, so that's this one here. The second equivalent of whatever, in this case, Br2, we're going to do multiple examples here, reacts with a pi bond, with the remaining pi bond, to make an alkane product. Right? So what you've got is basically because the alkyne has 2 pi bonds, right? So if we compare an alkyne has 2 pi bonds, an alkene has 1, the alkene pi bond does 1 addition reaction, right? The pi bond goes away and you make 2 new sigma bonds. The alkyne is generally going to do 2 addition reactions where 2 pi bonds go away and we create 4 new sigma bonds. So we're doing addition reaction followed by another addition reaction. So let's do another example of this, right? So here, first equivalent reacts to make an alkene, the second equivalent reacts to make an alkane, right? We can, if we're very careful, stop this reaction halfway through, right? So with bromination, if you are very careful and you say Br2 and you specify that you're only adding 1 equivalent of bromine, you will see only this product that comes out. Now notice that the bromines are opposite each other because you still get anti-addition, because it's still bromination, and so this will still give you the E-alkene as the product. And now we get to go back to some stereochemistry. We're pulling everything in this week. Okay, so you can do, if you add a single equivalent of Br2, you can stop at the alkene. But most of the time, we're going to add 2 equivalents and go all the way to the 4 bromines on there, right? Because this is easier because it'll react and then it'll react again. All right, so imagine what will happen if we take an alkyne and react it with HCl, 2 equivalents. Okay. The first thing that's going to happen is we're going to react one of the pi bonds and put a chlorine at one position, a hydrogen at the other, and we're going to get an R. Now, you may be thinking about Markovnikov's rule, right? Because anytime we use HCl, we have to worry about Markovnikov's rule. Markovnikov's rule doesn't really have much to say about alkynes because these R groups, both of these carbons are secondary, right? If we had a terminal alkyne, you would have to worry about Markovnikov's rule, right? So a terminal alkyne, we'll just do these right alongside each other. With 2 equivalents of HCl, you have a primary carbon here and a secondary carbon here. And so the chlorine will end up on the secondary carbon. And then the hydrogen would be here. But of course, what's going to happen next is the second equivalent of HCl will be added, and this is just an alkene adding to HCl. So your pi bond will come over and get your H+, you'll create a carbocation, and you'll end up with 2 chlorines on the same carbon. Now you always get 2 chlorines on the same carbon, and the reason for that is that the carbocation that would be created at this position where the chlorine is already attached would be more stable over here than it would be over here. So now that we're talking about an alkene, Markovnikov has something to say. You always form the more stable cation, and that's where the chlorine will end up. So you'll always get 2 chlorines on the same position, which is a good thing, right? It's nice to be able to predict that we don't have to worry about, oh, is it going to do something else? Obviously, if you treat this one with the second equivalent of HCl, you're going to get, once again, the chlorines are going to end up at the same place, Cl, Cl, and you're going to end up with, I guess technically you have 2 hydrogens here, you're going to end up with 3 hydrogens, so you'll have a CH3 group at the end here. Okay. So you have, again, it's the same thing. The first equivalent of HCl adds to make the alkene, the second equivalent adds again to make the alkane. We have a little bit more to think about because we have to worry about Markovnikov's rule just a little bit here because we're adding 2 different atoms, a hydrogen and a chlorine, right? But for the most part, that's not going to be. If we have an internal alkyne, the second chlorine just goes to the same as the first one, but the first one can go to either place because they're both secondary. With a terminal alkyne, the chlorine will go on the secondary carbon and then the second chlorine will also go there. So all of those are possible. Hopefully you see the pattern. The pattern is addition reactions look pretty much the same as they did in the previous chapters, right? Only now we're going to do them twice, right? With HCl or HBr or whatever, we usually don't stop this. Yeah, it's usually, usually not done with just one equivalent. And the reasoning behind that is that sometimes you'll get the E double bond where the chlorine and the R group, this would be the Z double bond where the chlorine and the R group are on the same side. Sometimes you get the Z double bond as I've drawn here. Sometimes you'll get the E double bond where the R group is down here and the hydrogen's up here. And those two are different compounds. And so if you stop after one equivalent, you're going to get a mixture of products. So usually it's better to just keep going because there is no E and Z, there is no R and S with a compound like this because you're not creating any stereocenters, right? So usually not done with one equivalent in order to avoid stereoisomers. Right, so it's easier to just do 2 equivalents of HCl and get down to this compound in order to not have to worry about R or S or E or Z. So we almost always use 2 equivalents of HCl or HBr or HI or whatever strong acid you're using. Right?